Hi, everyone. Hello. Okay, so can you see that? Yeah, you should be able to see that. Right. So today I want to talk to you about HTTP 2 and what that means in Servlet 4. Now, I quite like talking about HTTP 2 because it's actually quite an interesting major release of the protocol. So I'm going to spend some time talking about actually what is going on underneath the hood, because it is very, very different. Even though as a developer, perhaps you might not necessarily need to know that kind of detail, it is actually very, very interesting. And then towards the end of the presentation, I'm going to be talking about what that means for Servlet 4. Right, so before I start, I'm going to mention that I have some stickers, which you can all welcome to Java EE Guardian stickers. I have a large number of these, so by all means come and help yourself towards the end. So who am I? My name is Alex Theedom, and I'm a developer and have been developing for more or less 10 years. I'm also an author. I do training as well. I've just published some courses on lynda.com, also available on LinkedIn Learning as well. They are Java EE training courses. They're at a fairly basic level. So for any of your colleagues or employees who want to get up to speed with some enterprise Java technologies, by all means, sign up. And I'm a blogger, and I talk at various conferences. Okay, so that's enough about me. Let's go on and talk about what I'm going to discuss today. Now, I've got a little list here of things that I'd like to cover. So why do we need HTTP 2? I'd like to discuss why we need that and what are the motivations for having this major release. I'm going to talk about some of the workarounds that developers have implemented in order to overcome the shortcomings of the HTTP 2 protocol. And I'll have a look at HTTP sockets because that's actually quite important when we're talking about the changes that we have made in HTTP 2. I'm going to have a look at some of the top-line features. Now, there's a lot of stuff going on in this major release. So I'm just going to have a look at those changes that are particularly interesting and particularly important, the ones that have grabbed my attention and hopefully will grab your attention too. I'm going to have a look at Servlet 4 and what all of this means in Servlet 4. So I'm setting some ground by looking at the actual protocol itself, and then we're going to look at Servlet 4 in itself. Have a look at server support, because obviously you need to have a server that supports HTTP 2, what servers are currently supporting it, what versions. Have a look at current status update on the Servlet API. And if we get time, there's a few extra little bits and pieces at the end, which I can put in there too, which are quite interesting to look at. So, and questions and answers as well. So why do we need HTTP 2? Well, essentially, it's because when the web was developed many, many years ago, it wasn't really designed to deliver the kind of content that we're accustomed to experiencing now. You know, the original website was really very, very simple. It was nothing more than just text and maybe a few images, not even that. And this was what the BBC website looked like way back in, I think it was 94, so a very long time ago. And this is what it looks like this morning. Now, you can see quite substantially different. We have images, we have styles. It's a dynamic website that changes continuously. In fact, it's a website that really has nothing to do with what the original design of the BBC website was like. And this is typical of websites that we look at nowadays. And the problem with that is that the HTTP protocol was not designed to deliver the kind of content that we're used to now. It wasn't designed to deliver it at all. It's not suitable. And we'll have a look at why that is and what the sort of workarounds that we've created for that to overcome those shortcomings. And it's because really, if you have a look at the HTTP archive, it shows that the size of a website or a web page has increased 250%, literally since 2012, and that's only in the last few years. And average number of requests made to download resources, around 100 requests per page. And you can test this for yourself. You can go into Chrome and have a look at the network tab, and you can see that, you know, for each a refresh of the page, it downloads a large number of resources. I mean, the BBC website, I think, when I tried it the other day, downloads around 90 resources. The CNN website, I mean, several hundred resources per page. And that's not what the protocol was originally designed to handle. So, what are the problems with HTTP 1.1 or HTTP 1.x that we've resolved with workarounds and that HTTP 2 actually solves in a proper way? So there's this, the resources are requested in parallel. Okay, now anybody who knows that parallel processing is slow and ultimately results in blocking, because if the server does not respond quickly to the resources that it's requested, it blocks and it waits and it doesn't respond. And it takes time, it either takes time to respond or it doesn't respond at all. And this is what happens with HTTP 1.0 protocol, is that there's just one single connection, and over one single connection, you make one single request. You make the request from the client to the server responds to that request, and then another request is made, and so on and so forth. It's in parallel. HTTP 1.1 attempted to resolve this with pipelining, making multiple requests possible over a single TCP connection. However, the problem with that is that it didn't really work, or multiple-point browsers had problems implementing it. Firefox had implementation issues and dropped it. Chrome had similar issues. They also dropped it. There was inconsistency in the implementation of many of the features within HTTP 1.1. So essentially, we're really back to HTTP 1.0. And all of this resulted in what has been called the head-of-line blocking issue, which is where the server blocks further requests for resources, and the web page doesn't load or loads very slowly. And this damages the user's browsing experience. And particularly if you're downloading 100 resources per page, you can't sit there waiting for every single individual resource to download. Eventually, you're going to get fed up. And we all know how important it is for the browser experience or the experience of the user to be a really good experience. You know, milliseconds cost businesses millions of pounds. We've seen many of those statistics. Amazon published some statistics a few years ago on that topic. So what are the workarounds? Now, front-end developers have been very clever and have really done themselves proud, one could say, in developing workarounds to these issues. So let's have a quick look at some of these workarounds. So instead of having one connection, you have multiple connections. So you open up one connection to download your style sheet. At the same time, you open up another connection to download your JavaScript, and you open up another connection to download your images. Now, that's great if you've only got 3 or 4 or 5 resources. If you've got 100 resources, that becomes a problem, and we'll have a look at why that is later on. It kind of fixes the problem a little bit, but it really, again, it is just a workaround. And the real issue with this is that TCP connections are expensive. Every time you create a connection, it costs time, it costs effort, it costs resources. Ideally, what you really want is one single connection, and you do everything over one single connection. That would be the most efficient use of the TCP sockets. And to add to this issue is that browsers specified a maximum number of connections to a particular domain and specified it inconsistently. So different browsers specified a maximum number of connections to the server or to a particular domain. So your browsing experience, or the quality of your browsing experience to some extent, was determined by the actual browser itself rather than the design of your site, which really shouldn't be the case. So let's have a look at ways around creating lots and lots of connections. So one way is to concatenate your files. So you would, for example, you have 3 files, 3 CSS files. What do? You concatenate them all into one great big file. Okay, that works. You have 3 connections, now you have 1 connection. That works from the point of view of creating connections, but it's not really very good design. Alternatively, you could inline your CSS and your JavaScript. So going from that to, for example, this. Now, this scares the hell out of me. I would never want to work on a site that developed front-end technology in this way, because you are embedding styles, you're embedding JavaScript right into your into your HTML, and it's just not maintainable realistically. On top of that, you can actually even embed images. So you base64 encode your image, you copy and paste this ugly string directly into your page, and you've got an embedded image. This, again, resolves an issue with regard to creating connections, but it's not very efficient. It's time-consuming to decode, and caching is a bit tricky. Again, these are all kind of workarounds that over the last few years, whether they're popular now or not, have been developed in order to get around this issue, this fundamental issue of creating connections, which is expensive and limited to the number of connections that you can have. Alternatively, create a sprite sheet containing all of the images. When that sprite sheet is downloaded, one single connection for that image, and you cut out all the little images. You cut out all the logos and the icons. I mean, this is an actual one from Amazon, then you've got one from Google, another one from Facebook. So this is what people actually do. This is what companies have actually been doing. And even big companies, they recognize that this is actually a valid solution or a valid workaround to this issue. But then again, if you can have a maximum of, say, 10 connections to one domain, if you have 2 domains, that means you can have 20 connections. If you have 3 domains, you can have 30 connections. So why not just have lots of domains? I mean, why not? You can do that. But then again, you're creating this big back end of how many domains have you got. And if you're downloading 100 resources per page, how many domains are you going to have? And this really, it solves the problem. I mean, you get around this issue of browsers specifying the maximum number of connections to a particular domain. But again, it's a workaround. You're letting the front end control what's going on the back end. Again, those two things, in my opinion, should actually be separated, really. So let's talk about HTTP sockets. So what does the specification actually say about sockets? So TCP sockets, I should say. Well, HTTP 1.1 doesn't really say a great deal. It doesn't really seem to consider it a significant issue, and really just specifies 2 maximum. 2 maximum sockets should be opened. Of course, that's ridiculous. You can't possibly have a modern website with only 2 TCP sockets. But browsers completely ignored it anyway and just did whatever they wanted to, and inconsistently implemented maximum download, maximum connections. And it's kind of seen, really, I suppose, this really means that it's seen as a throwaway resource. A resource that you can open, you can close, you can open, you can close, it doesn't matter. It's not specified how it should be treated, which is contrast to the way in which HTTP2 sees this particular issue. A lot is said about sockets. What it says about sockets is that it's a scarce resource. They are something that should be respected. You only actually really want to open one single socket, okay? And you might be saying, well, how is that going to be possible? How can you open one single socket and do all the things that we need to do to download all these resources that modern websites need? Well, we do that because we fundamentally changed the way that HTTP2 works under the hood. Now, let's have a look at some of the top-line features that allow us to use just one TCP connection and to still have the kind of rich website experience that we're all accustomed to. So HTTP2 is comprised of 2 specifications. So you've got the HTTP Transfer Protocol version 2 specification, which is largely based upon work done by Google and the Speedy protocol. They did a lot of really excellent work and proved that it was possible to do what is specified in this protocol. And also there's HPAC, header compression. This is about reducing the duplication between requests and responses in the header information. Okay? And there's a lot of duplication, and we'll see what that duplication is a little bit later on in a couple of slides to come. And most importantly of all, the reason why this is all possible over a single TCP connection is because it's a binary protocol. Okay? It's binary, it's not text, it's binary. Okay? Now that means a lot of different things, and we're going to have a look at some of what that means coming up right now. So, you've got a single connection, you're going to have request and response multiplexing. Okay? You have request and response go over a single connection that's got to be multiplexed. It's the only solution to the problem. And that is achieved with binary framing. Okay? So your request and response are broken down into frames, and we'll have a look at that a little bit later. This is just an overview of the headline features I'm going to be discussing. Header compression, we just discussed that. That's about reducing duplication in headers. We'll have a look at that in a moment. Stream prioritization is about prioritizing resources. So what are the resources, what requests are going to be dealt with before other requests, giving prioritization to certain resources rather than others. And server push, which is probably the most important thing from the point of view of Servlet 4, because this is about pushing resources to the client before the client actually requests them. So it's about anticipating client requirements and we'll have a look at that as well. So, most important feature is request and response multiplexing. This allows us to resolve the head of line blocking. And we'll see that later. And it's fully bidirectional communication over a single TCP socket. And it's done by breaking things down into frames. So let's have a look at this. We start with our connection, with our TCP socket. Okay, so we have one single socket. Over that socket, we have streams. These are logical streams of communication, channels of communication. Within those streams, you have messages. These are the messages which are our request and our response, which we all know and love, and some control messages, okay, that control various things about the communication. And then we have the frame, the binary frame, the smallest unit of communication. Now, the binary frame is essentially a message, a response or request message, broken down into its constituent parts. And we'll have a look at that in a moment. And all of this resolves, like I said, the head of line blocking issue. And that's really actually what all this is about, largely what this is all about. So sometimes it helps to see an image. I don't know about you, but I love looking at pictures. And a picture can explain something very easily. So again, you can see here, you've got your connection. You've got within that connection, you've got your streams. Within the stream, you've got the message. And within the message, you've got the frame. So messages are broken down into frames. Messages travel over streams, dedicated stream for that message. And those streams are logical streams over a single TCP connection. So let's have a look at another graphical representation of what this is all about. So breaking things down a little bit more, we interweave, and this is where the multiplexing comes, we interweave our logical streams over a TCP connection. Now, let's have a look at this image just for a little bit. Now, what we're doing here, we have the browser on this side, we have the server on the other side, and you can see, if you have a look at stream 1 is sending a frame, and I should say that each one of these arrows is a frame, okay? And in that frame, it identifies itself as belonging to stream 1, and we're looking at the far left here, and it's of frame type headers. That means that this frame, this packet, however you want to imagine it, contains header information only for this particular response. And you can see here on the other side, you've got the data for that response. So you're not sending, in a traditional sense, the header and the data in one big packet to the browser. You're actually breaking it down into a header frame and then potentially various data frames, depending on the size of the data that you are sending back. But also look here as well. We have stream 2 headers are being sent, and then stream 2 data immediately after it. These are the responses interweaved. So you've got two responses coming back to the browser, interweaving themselves. Okay? It's not the same as with HTTP 1.1 or 1.0, where you have a request and a response, then a request and then a response. What you have here is request, response and request, and response and request, all interweaved in their little parts, because they've been broken up into their constituent parts. So they've been broken up into headers, they've been broken up into various data parts or data frames. And what the browser does is it collects together all of these frames and reconstructs the actual response. Now, at the same time that the server is sending responses back to the browser is sending requests, as you can see in stream 3, to the server. So you've got a header and a data. And it's always broken up like this. So headers are separate from data. And And it's worth mentioning as well that a request and response is mapped one-to-one with a stream. Okay? That's actually something that is not always made clear, but it is mapped one-to-one with a stream. So a stream is kind of like an identifier, a stream identifier. It's actually referred to as a stream identifier. It's a way of giving the parts of the puzzle the same identity so that they can be reconstructed at one end or the other. So let's decompose things just a little bit further, and I'm not going to go any deeper than this because I think this is the deepest level you can go to, because this is the frame. Now, a frame has various fields. The ones that I want to focus on are the four things here. Type, which is going to be headers, data, and various others, which we'll have a look at in a moment. And stream identifier, which is going to be stream 1, stream 2, stream 3. So the stream that this frame belongs to, plus then you have the payload, which will be the data if it's a response, for example. And then a flag, which is going to be the obviously 0 and 1, on or off, which identifies whether this frame is the last of its type. So you might have several data frames because you're sending back a very large image, and that's been broken down into, say, 3 frames. And you're going to want to identify which one of those is the last one. Okay, so that flag identifies the data frame or the header frame as the last one in that sequence. So what types can you have? So headers, they correspond directly to the HTTP headers that we all know and love. Data corresponds to the data. Okay, now that's easy to understand. These other frame types, what are they? These are new ideas. So push promise and RST stream, that relates to the concept of server push. So push promise, which we'll have a look at later on, is the server telling the client that it wants to send it a resource. So it sends a promise or a request for permission to send the resource. Obviously, you can't have a situation where you've got servers just sending whatever resources they want to a client. The client has got to have the veto, and it's got to be able to send back a request saying, no, I don't want that resource. So it sends back an RST stream, and these are just names of types of frames. So the client will send back an RST stream and say, no, I don't want this resource that you want to send me because I already have it. I already have that in my cache. I don't want it. Don't send it to me again. Or I don't want it because the user has moved on to a different page or something like that. And there are various other frame types as a priority. This relates to stream priority, and this gives the server an opportunity or the server or the client to offer opportunity to allocate a certain number of resources to deal with that particular request. And there are various other configurations, setting ping, go away, and various other things which I won't go into right now. So let's have a look at header compression. Now, let's start by mapping the traditional HTTP request with what a header frame looks like. And this on the left, you can see, is a very simple representation of an HTTP request. You've got a GET request to an index HTML page. And here is on the left-hand side the header frame, or what a header frame would look like. So you've got the frame type, which is headers. You've got the flag, which is going to identify whether it's the end of the stream or the end of the headers. That's the flag I spoke to you about earlier. And then you've got various pseudo headers, which represent the actual HTTP headers. So that you can see they map one-to-one quite easily. So the response to that, so the traditional HTTP response is, as you can see, quite simple, with the payload, may the force be with you. The frames are divided into 2 frames. So you have one header frame, which contains just the header information, and you have another frame which contains just the payload, which in this case is just a simple text message. And you can see again the HTTP header mapped one-to-one. So where does all this come into HPAC and header compression? Well, there's a lot of duplication between request 1 and request 2. And you can see that the method is the same, the schema is the same, the host is the same, the authority is the same, everything is the same between requests from the same client to the same server. The only difference is the path. So why are we sending every single time the same header information? Ideally, you won't be doing that. Ideally, what you do is that the first request that is made to the server is a full request with all the header information in it. The second request only contains the delta, only contains the difference. Now, there's a lot of stuff going on underneath the hood, effectively, to make this work. So both the server and the client have tables of header data that was seen in the last request or response. And it does a matching to match up what was seen before. And therefore, in this second headers frame here, it knows that the method is get because the previous one was get. It knows the schema is HTTPS because the previous one was HTTPS, and so on and so forth. So this is HPAC, and it compresses the header by reducing duplication between requests and response. And that actually saves quite a lot of resources going backwards and forwards, and makes the header frames much smaller. So prioritization. Let's look at this very quickly. Again, prioritization can be specified hierarchically. It's literally just a number that represents a percentage of resources that needs to be attached to each stream. Now, the priority is either located in the header frame or it's in its own priority frame. And we saw earlier that there was a header type called priority, and that's where it could be specified. So 2 places where the priority for this particular stream can be specified, in the header or in its own special frame. But it's only a suggestion. It can be completely ignored. Okay, we don't want to let the client control what the server is doing. The server is best placed to know how to allocate resources. So it's just a suggestion. And the server can completely ignore it if necessary and if it deems fit to do so. So server push. Now this is the part of HTTP2 that is most visible in Servlet 4. And what is this about? This is about eliminating the need for inlining resources. Okay? It allows the server to analyze what the client wants and proactively send to the client the resources it needs. Now, when I'm saying resources, what I'm talking about is a simple HTML page which has a need for some images, some CSS, and some JavaScript. Okay, fairly simple. And how does this work? Oh, hang on. Oh, did that work? Oh, yeah. Okay. So can I just go back? Okay, so you've got an HTML page. A request for that page is sent to the server. Okay. The server analyzes that page in some way, however that's implemented. It analyzes the page, and it sees that it needs a logo image. It sees that it needs a style sheet. It sees that it needs some JavaScript. And it starts sending those resources. It starts sending the image, the logo image, back to the client. It sends the CSS to the client. And then it sends the final processed HTML page back to the client. Now, obviously, this is a very simplified explanation of what it does, because you can imagine a situation where you have a page, there's some quite complicated business logic going on in the back end. That takes a few milliseconds to process, but while that's being processed by your back end, your servlet layer is sending these resources to the client in anticipation that the client will need them. Now, we saw previously about Server Push, and we saw about the RST stream. This controls how the server can send it back. So the server makes a push promise. The client says, yes, I want that resource, and then the server sends that resource. Or the client can reject the resource if it's already in the cache. Oh, yeah, so I'll put that here. So, yeah, push promise is sent in order to advise the client that a resource is coming. And the client can reject it by sending a different frame back. So what does this mean for Servlet 4? So server push is probably the most visible improvement in Servlet 4, because it actually is probably the only thing you're really going to be seeing, because actually a lot of this stuff it all happens under the hood. You know, you're not really going to see a lot of this that I've been talking about, but it's very interesting to know what is really going on, so you can understand how this kind of all works. So Server Push is implemented in the servlets because it's the best place to implement it in the servlet layer, because it's generally the best place to implement this, because that's where the requests come into, and that's where frameworks are implemented. They implemented around servlets, essentially. JSP and JSF, they're all around servlets. So this is the best place where it should be implemented, which of course is where it is implemented. And essentially looks like this. As a server push, you have a push builder. You build up a push object, and you call various methods on the instance, which you obtain from the request object. We'll have a look at an example in a minute. So this is essentially a sequence diagram. So I think I might be laboring the point a little bit, but I want to make this really clear that the browser requests the index page. We've seen that already. The server discovers a need for a CSS and JS file. We'll see how it discovers that later. And that depends largely on the framework that you're using and how it's implemented. And I'm going to talk about a couple of ways it could possibly be implemented. You get a push builder. Now, this can be done manually, or it can be done under the hood. And from that, you get that from the HTTP request. You set on the push builder instance the CSS file, and you invoke push, okay? And you call the push method. So either you're doing that yourself as a developer, or it's been done under the hood by the framework. Again, you do the same thing with the JS file that you've discovered you need, and that is pushed. And then it responds with the index HTML file, or whatever the response happens to be. I'm just keeping it simple here. Again, like I said, the push builder is an object that can be reused. You don't need to create a new instance. So you got one instance from the request, from the HTTP request object, and you can continually reuse it. So let's have a look at this in a little bit more detail. So it is constructed with it's constructed with a single method, which is set to get. And there's only one method that it can be set to. That's done by default. Various things are stripped out: condition, range, expectation, authorization, request headers. These are all removed. They're not needed for the response. Cookies are only added back if the max age is not expired. Okay. And the only actual requirement is to specify the URI or path of the resource you want to send back. Now, this is done by yourself, or again done by the framework. Now here we have an example of how this could be implemented. Now this is really simple. Okay, you wouldn't be doing this really. So you have here a servlet. You've got your do-get method that receives HTTP servlet request. From that, you get the push builder. On the push builder, you set the path, like I said before, to the image, and then you call push, and that's it. It pushes it. Okay. A lot of stuff happens underneath the hood, because obviously it sends out a push promise frame, and then the client has to respond, and so on and so forth. So there's a lot of stuff happening underneath the hood, but the only thing from a programming point of view that you need to care about is just calling that push method once you've set the path to your resource. So let's have a look at more or less the same example. But one thing I want to point out here, which is quite interesting, is that it is possible for the client to configure not to participate in any push requests. Okay. So here I am just calling is push supported. It might be, it might not be. There's no point in trying to push something if it's not supported by the client in the first place. And the client can choose not to support it if it wishes. That's up to the client to specify. And it specifies it in a frame when it makes the first connection to the server. So let's have a look at a bit more code. Okay, this is a slightly more intelligent way of implementing this. You wouldn't necessarily write this directly in your servlet code. You'd actually probably implement it as a filter. Now, this is actually how it's implemented in Jetty. Now, Jetty's had support for this for very long time. So I've got the packages org.eclipse.jetty.servlet package. There is a push builder filter that intercepts every single request, analyzes the page, and actually does all of this for you. This here is a very simple implementation. The actual code that Jetty has written is this big, so I haven't got room for that. But this is, again, very, very simple. You are in your filter. You've got access to your servlet request object. From that, you get your push builder, and you continue as you've done before. So you're setting the path and calling push. So obviously, web frameworks are the most important use case for this. They will obviously be using this substantially. JSF has taken advantage of this because it kind of depends on knowing what resources the client needs. So obviously, the first interaction that the server application has with the client, that's where this is going to be implemented, and JSF is where it's going to be implemented. And as I said before, frameworks are best placed to deal with this. So JSF is a framework which deals with this elegantly. And you don't need to do anything. Okay, you get it for free. So essentially, you've learned all of this, but you don't really need to do anything because you get it for free with the latest version of JSF. You don't need to write any servlet filters. You don't need to actually change your code. Really, you don't need to do anything. You just use the latest version of JSF, and you get it for free. Okay. So, like I said before, a client can enable or disable server push by sending settings enable push frame on the first connection to the client. It can reject any push promise if it doesn't want the resource, because it has the resource already in its cache, or for whatever other reason, it can do so. And the servlet container must request that. Of course, you can't have a situation where the client says no, and the server goes, I don't care, I'm going to send the resource to you anyway. But again, this is all happening underneath the hood. So, Servlet 4 features, perfectly backward compatible. You don't actually really need to do anything. You can use it out of the box as it is. Just upgrade to Servlet 4 and you're fine. But you might want to consider reworking all the workarounds that have been developed to deal with these kinds of issues. So if you have domain sharding, if you have inlined resources, if you have implemented some of these workarounds, which are pretty common, you might want to reconsider, or you might want to consider stripping those out and refactoring your code on the front end. And there is a possibility that if you don't, you're not going to fully benefit from the features of Servlet Push. Okay, so that's something that needs to be taken into account. Now, this is really very early days on this, and it's not something that I've read a lot about or I've spoken to a lot of people about, because there's not a lot of people really doing a lot of this. So we're not quite sure how much refactoring is really necessary to take full advantage of these changes in Servlet 4. This is something that, we're going to be discovering. And also, I think as well, we're not quite sure how to best optimize for HTTP2. Again, this is something that we all have to work on. I mean, there are various things that one can do to ensure that we are taking full advantage. But again, that's something that we need to consider going forward. So like I said, JSF developers do nothing. So if you're a JSF developer, you're happy. So server support, basically everybody supports it. That's the idea. So Glassfish 5 has nightly builds. They have the reference implementation obviously supports it. Pyro 5 doing a good job with their Java EE8 development branch. Jetty, stable version 9. I think it's probably an even newer version than that. They've had support for server push for forever, what it seems like. So this is the push cache filter, which I spoke about earlier. That's their implementation. Really interesting. Have a look at that code. It's worth looking at. Wildfly 10, Undertow, has a support in the master. Tomcat 9 again, has a push builder support in the serverless HTTP package. And NetE4 generally has taken 4.1 has taken full advantage of HTTP2 and implemented most of the headline features. So, status update, I'll go through this quickly. Yeah, so as of 23rd of May 2017, in public review ballot status, it's going to happen. Issue tracker, if you want to know what the current issues are on the servlet spec, you can find it there on GitHub. JCB specification 369, if you want to read about the implementation of it. And there is a Twitter account, which is a bit sleepy. Occasionally, you might find some things published on that. Extra bits. Now, I want to have a look at this because these are fun bits. Okay, so the goal of HTTP2, as we know, is to improve the perceived web browsing performance, but we actually need to make sure that we're not kidding ourselves and this actually really does work. So, go to that URL. Go there right now and have a look at their really nice and neat little tool that they have, which gives a very nice demonstration of just how much faster or how much more performant HTTP2 is over HTTP 1.1. Again, there's another little tool that you can go and play with that compares HTTP versus HTTPS. I prefer that in there because that's actually quite an interesting tool. Now, there was one thing which I wanted to mention, and I took the slide out because I thought I was going to overrun, which I might be. No, I'm okay, I've got a couple of minutes. Is TLS. Is in the HTTP2 specification, it does not specify whether HTTP2 requires TLS or not. It doesn't require it in the specification. Okay. Speedy did, and that was a requirement of Speedy. It required TLS. HTTP2 doesn't in the specification. However, every browser implementation of HTTP2, that's HTTP2 compatible, requires TLS. Okay? Even though the specification allows connection that is unsecure over HTTP2, you won't find a browser that allows it apart from Opera Mini, which doesn't seem to participate in anything. So that's actually very interesting because that now forces everybody to use TLS for every single site if they want to use HTTP2, which personally I think is great. You know, we want all of our web communication to be encrypted for obvious reasons. But I thought I'd mention that because there is a new upgrade protocol. You can't use the traditional 101 response. You'd have to go through, I don't have details on that here, but you'd have to issue a special request, and it's dealt with on the back end, and upgrade is handled based upon the capabilities of the server and the capabilities of the client. So the client advises the server of its capabilities, and the server chooses the one from the top of the list of its capabilities. Useful resources. Okay, if you want to know more, have a look at this Git book. It's an excellent explanation of HTTP2. Free O'Reilly ebook. This is excellent as well. I strongly recommend that you get a copy of that. And there are some very nice frequently asked questions here on this GitHub page. Ah, I made it. Okay. Questions or answers? If you have answers also, I like answers. Yes?
Can you say something about browser support today?
Everybody supports it, apart from Opera Mini. Yeah. So that question was about browser support. Every browser supports HTTP2 in their latest version, apart from Opera Mini, which doesn't. Well, I am not sure about Spring, but if Spring, I'm not a Spring developer, but Spring is built on servlets. If Spring is, as far as I can, correct me if I'm wrong, but Spring is built on servlets. If they're built on Servlets 4, it gets it automatically, I believe. Spring developers will be able to tell you. Spring 5 definitely has support for HTTP2. Exactly how, not entirely sure, but I do remember reading a couple of weeks ago that Spring 5 does have full HTTP2 support. Other frameworks, I'm not sure if you're talking about MVC 1.0. Are you talking about that? Because that uses JAX-RS behind the scenes. So that's actually a question I had. I was discussing that with Ivor a couple of months ago, and waiting for him to come back with an answer on that one. Yes. How does that comply with the server should be stateless? It doesn't. Servers aren't really stateless. I think if you're talking, you're talking about, for example, HPAC, which is the header compression, because the server has to maintain some degree of state about what headers were seen before. So, I mean, someone asked me this question before, and it's kind of, well, server, it's not really stateless. You know, from a practical point of view, if the server has to maintain a table of previously seen headers for that particular client on that particular request, it's not, is it? It's not stateless. Yes, the TCP connection is maintained open. So the client will initiate the connection. There's various initialization communication that occurs, communicating various things. You make the first request, and the server will record, for example, the headers, and that connection will remain open for as long as the tab or the browser is open, or as long as the connection needs to be open. And then when it's closed down, then that's finished. Yeah, I don't think nothing's maintained after that point. I mean, the exact implementation of that, I have to admit, can't be 100%. It's a very good question. I don't know. From what I understand, indefinitely until it's closed. And I'm not sure if there's bound to be a timeout. And to be honest with you, I can't remember what the timeout is, but there will be a timeout. I'll have to check the specification for that particular detail. Yeah. Now that's a good question. Now, based upon what I understand, is that it's done by hops. So you got the HTTP proxy here, the client here, and you got your server there. It's done by this hops here. So between here and here and here and here is a separate. So if you're talking, for example, take the same example of header compression, it's between here and here that you've got the connection, then between here and here. So it's not transparent across when it comes to HTTP headers. As far as my reading of the specification. Now, don't hold me to that. I would have to. That's a very specific question. I'd have to get back to you on that one. Anybody other questions?
Thank you, Alex.
Thank you.
To be brutal because there's lunch. So.
Oh yes, sorry, I'm keeping you from your food.
But it was brilliant. Thank you.
Okay, thank you.